Pair production is defined to be the conversion of a neutral boson particle into a subatomic particle and its antiparticle. Some examples of subatomic particles and their corresponding antiparticles are electron-positron, muon-antimuon, proton-antiproton. One common example that we shall illustrate in this video is using a photon as a neutral boson particle to create an electron-positron pair. The process occurs in the presence of a nucleus as illustrated in the following animation. Basically, a positron is a subatomic particle having the same mass as that of an electron, but of opposite charge. It constitutes the antiparticle of an electron. Here three main questions may arise. First, why positron was created? Second, can any photon create an electron-positron pair? And the third question, can the process occur without a nucleus? Let's start answering the first question, why positron was created. As far as we know, electric charge must be conserved in every physical process. The photon has no charge, while the electron on the other hand has a negative elementary charge. After the interaction, the charges must sum up to zero according to the principle of conservation of charges. Then there should exist a particle that has a charge opposite to that of an electron, and this particle is a positron. Now, for the second question, can any photon create an electron-positron pair? The simple answer is no, energy must always be conserved. Let's consider the case of least energy, where the electron and positron are created at rest, that is, they have no kinetic energy. The total energy after the interaction is the sum of the rest mass energies, which is 2m node c squared, about 1.02 MeV. In order to create such particles, a photon with energy of 1.02 MeV is needed. This value is considered the threshold value of energy. If the photon's energy is below the threshold, then no pair is created. If it is equal to the threshold, the pair is created at rest. If it is higher than the threshold, the pair is created with some kinetic energy. Now for the final question, can the process occur without a nucleus? Again the answer is no, since this would violate the principle of conservation of momentum. To make it clear, imagine the process occurs without a nucleus, then the conservation of energy would give the following. And the conservation of momentum on the other hand, would give the following. Comparing these last two equations, we get, which is simply impossible, because as far as we know, nothing can reach the speed of light. So as a conclusion, pair production is possible if a third particle is available to carry off the excess of momentum. So we usually use a nucleus, and please note that the nucleus has no active role at all, it only contributes to the conservation of momentum in order for a process to occur that would otherwise be forbidden by the conservation laws.